As we kind of wrap up this chapter, we're going to look at some kind of trends in acidity and basicity. And by trends, we're going to really look at the periodic table. And we're going to see that acidity can kind of be predicted by a couple of factors. The first factor in predicting an acid is the polarity of the H whatever bond, the HA bond. As we know, as A gets more electronegative, it ends up hoarding the electrons. And we're going to see that the bigger that polarity happens to be, the stronger the acid will be, generally speaking. And these are rules of thumb. These are kind of trends that we're going to see. So we're going to see that as polarity goes up, the acidity goes up as well. Meaning that Ka goes up or the pKa goes down, whichever way you're looking at it. For example, if we consider these two, the difference in electronegativity for these, with oxygen is 3.5, we're looking at a difference of 1.9, or for water, it's 1.4. We also know HF is hydrofluoric acid, and H2O is, of course, hydroxic acid, or we could just say water, but I can be funny. We know that HF is a stronger acid than water is. We see that because of the difference in polarity here. The HF bond is much more polar than the HO bond, and as a result, the HF bond will be more acidic. So bond polarity figures in here, and the trend is as the polarity increases, your acidity also increases. The second trend, which is somewhat more important, is the HA bond strength. And essentially, the bond strength, remember, is the amount of energy it takes to break the bond. So when we want something to be acidic, we want it to have a relatively low bond strength. So as bond strength goes down, acidity will go up. And in this, we can compare HF, HCl. We know that HF is a weak acid, HCl is a strong acid. If we take a look at their bond dissociation energies, which I have written somewhere here, 567 kilojoules per mole for HF. So this is the amount of energy needed to break these bonds. And then for HCl, we're looking at 431. We can see here very clearly by looking at their bond strengths that the HCl is much weaker than the HF bond. And we also know HCl is a strong acid, but HF is a weak acid. And so if you see this trend, by the way, HI is in fact going to be our strongest acid. And I have the numbers here. I don't know that will be very useful, but we have 299 kilojoules per mole for the HI bond. And the HI bond, as we know, is going to be still fairly polar because we have a hydrogen and a pretty electronegative atom. And just to complete the table, we'll have the bromine here at 366 kilojoules per mole. So we are going to see that HI is going to be the strongest of our halo acids. And in fact, HI is pretty much our strongest normal acid anyway. So fun stuff there. So as bond strength goes down, acidity goes up. And then the last thing, the last factor in predicting the acidity is very important for OChem. So if you're going to take organic chemistry, this is the one you're going to focus on the most. Is that the stability of the conjugate base. So when we're looking at these, for example, if we can consider acetic acid, and we're looking at that proton there on the right, versus something like ethanol, also looking at the proton on the right. The pKa of acetic acid is around 5, and the pKa of ethanol is around 15. If we look at the bond strength and the bond polarity, they're roughly the same because these are all OH bonds. But the pKa of the acetic acid is much lower than the pKa of ethanol. The reason for that is because if we look at the conjugate bases, once we remove those protons, and in fact, I'm going to go ahead and put in our formal charges and all that fun goodness in our lone pairs, we see, in fact, that the molecule on the left there can resonate. And in doing so, we have different resonance forms that come out. And this is a very important factor in stabilizing the conjugate base. Because we're able to move that negative charge around, it stabilizes it. So our negative charge now is on the other oxygen. So we're able to kind of move that around. We're going to see later on, if you take OChem, that anions are pretty unstable, at least for organic molecules, carbon-based molecules. And so the ability to resonate that around, this is resonance, remember, multiple Lewis structures that can be formed for the same molecule, greatly stabilizes a molecule, greatly. The ethanol does not have any way to resonate that negative charge away, and so it's stuck like that. And so it is not stabilized. So if you can stabilize the conjugate base, like through resonance, for example, in OChem you'll learn a lot more ways of looking at the stability of the conjugate base, but resonance is a big one. And you can see here already, that's a 10 to the 10 difference in their acidity. That is, 10 billion difference in their acidity. So acetic acid much more acidic than ethanol is. All right, so the stability of the conjugate base is also a factor here. And so we can look at some trends. For binary acids, that means just HA, 2 atoms, that's it. For binary acids, we see that as we go down the periodic table and to the right, down here to iodine, see, we've got oxygen, nitrogen, carbon. As we go to the right and down, we have acidity increasing. So HI will be our strongest one. HBr is going to be kind of our next strongest one, then HCl, HF. Generally speaking, the sulfur and the phosphorus, H2O, as we know, is kind of our standard point for acidity. It's one of the very weakest acids. After that, nitrogen actually becomes a base. So NH3 is a base. CH4 is nothing at all. It will not ever react as an acid or base. Phosphorus is an extremely weak base for pH3 phosphine. H2S is ever so slightly acidic. More acidic than water is, but still not very, especially compared to HCl. So for binary acids, where A is any of these elements, on the periodic table, we see that as we go to the right and down, acidity goes up. For the two factors of the electronegativity as well as the size, because the size is going to help determine that bond strength. So HI will be our strongest acid again. For oxyacids, though, we can do some comparisons. If we're to compare the like hypochlorous, hypobromous, hypoiodous acids, we're going to see that when we're looking at oxyacids, we're looking at the electronegativity of the atom to which the oxygen is bound. We might write the acids as this way because that's how we learned our naming. But really, if we take a look at the Lewis structures, we have the oxygen in the middle, bound to the hydrogen that is acidic, and then you've got the chlorine there. and the structure is analogous for the rest of them. And with that, when we remove that oxygen, or that hydrogen, we're looking at the bond strength again, right? And we're going to see that the bond strength differs with the electronegativity of the kind of other atom, the atom that's not oxygen. We're going to see that this one is the most acidic of the three. This one's the least acidic. And the trend here is about electronegativity. So it's the most acidic because Cl is the most electronegative. So if you think the electronegativity means it's helping to pull electrons towards itself. So chlorine pulls more of the electrons from oxygen than bromine would. And as a result, because the oxygen's electrons are being slightly taken away, even though oxygen overall is more electronegative, we're looking at the other side now, chlorine can pull a little stronger. Even though it's not as strong as oxygen, it's stronger than bromine or iodine. And as a result, it can pull those electrons a little bit away more, which weakens the OH bond. So as the OH bond gets weaker, it's easier to remove, and therefore it's more acidic. So for oxyacids, for the same oxidation state, we're looking at electronegativity. And then finally, we'll look at one more trend here. When we have the same atom, multiple oxygens on it. I guess we need to put some lone pairs because we're being good chemists. Oh my goodness. Okay, forget it. I'll only put the lone pairs on the chlorine. We know that perchloric acid is a strong acid. None of these other oxyacids as drawn are acidic. Strongly acidic, that is. They are all weak acids. We're going to see that as oxidation number increases, for example, the oxidation number of the chlorine here is +7, +5 here. For the hypochlorous, that's actually +1, and then we have +3 for that one. As the oxidation number increases, our acidity will also increase. So if you want to think about it, in perchloric acid, the very bottom right there, those 3 double-bonded oxygens are stripping away all of chlorine's electrons. Right? That poor chlorine has so few electrons, it's going to try and take as many electrons, or electron density, from the oxygen that has the hydrogen as possible. Like the electrons are being pulled away from the chlorine, right? They're being pulled in all these different directions. And so that poor chlorine's all like, please give me some of your electrons. And as a result, that OH bond decreases in strength, thereby making it more acidic. So, couple trends. For binary acids, H and one other atom, whatever it may be, or something like H2S, just still 2 atoms, so it's still diatomic rather, in terms of the identity of atom. Those increase to the right and down along the periodic table. So iodine is your strongest acid, binary acid. If you're looking at oxyacids, you want to look at the electronegativity of your central atom, the one to which oxygen is attached. And when you're comparing within that, highest oxidation state also wins. So lots of factors here. So just general trends, again, most of this stuff will come back in organic chemistry, and it will be very important there. So if you're planning to take that, this is a very good place to start learning these trends.